I am a big fan of Bluebikes, but let's be real, sometimes they can drive me a bit crazy. Like this one time I biked from Harvard to MIT and guess what? Not a single spare dog at MIT. If I wanted to return the bike, I would have had to bike all the way to Boston and then walk back. And yep, that extra riding time means higher fees. I think they don't want me as a user anymore. Bluebikes face a natural challenge, the imbalance of bikes' arrivals and departure at each station. Every day, the operation team has to relocate bikes around to maintain service quality. This involves pickup, drop-off, and truck fees, which all add up. Let's dive into some data from Cambridge, focusing on March 15, 2024. Here's a cumulative diagram showing bike movements. Notice how the departure curve is higher than the arrival one. This indicates more bikes are leaving than arriving at the station. That's how operation teams work. If bikes aren't redistributed promptly, it frustrates users, both those wanting to borrow a bike and those needing to return one. My project aims to minimize these frustrations by reducing the operation cost of both bikes. Different times of day see different biking patterns, so the optimal strategy needs to be flexible. I have broken down the day into certain time segments from 8 a.m. to 8 p.m. and calculated the arrival and departure rate of each station. This leads us to a mixed integer programming problem. Planning truck routes and deciding whether to redistribute bikes at each station or lose customers. At each hour, each of the N stations in Cambridge would be evaluated as to whether the difference in number of initial bikes at that hour, EI, and the ideal range of bikes, II. The ideal number of bikes was set around 70% of the capacity of each station, and this could vary by 3 bikes, positively or negatively. Also, I set a binary value to indicate whether there is a bike surplus or shortage at station, which represent the situation of potential customer loss. Thus, each hour, depending on which station needed to be redistributed, the truck would make a different sequence of passes through the station Xij, yielding a different distance Dij and the number of bikes redistributed. Our goal is to minimize operation cost. Calculate as the formula shows in the slide, where B is bikes relocated, D is distance traveled, and C is unhappy customers. We ensure each station is visited optimally, avoiding unnecessary loops and maintaining ideal bike numbers. Using Groby, I calculated the daily operational cost for a week. Demand fluctuates between weekdays and weekends, with peak hours needing more attention. Sometimes, it's less costly to let the stations remain unbalanced and lose potential users than to rebalance it. Comparing the optimization strategy of sacrificing a certain number of customers with the strategy of fully ensuring customer satisfaction, sacrificing a certain number of customers can greatly reduce the operating costs of Bluebike. I understand why I can't find an empty dog at MIT anymore. There are still many issues with the model. For instance, the truck's capacity and transport time should both be considered as variables in the operation. Additionally, users' decisions vary depending on the actual circumstance when facing stations that cannot provide service. For example, whether there are nearby stations that can meet the demand or if there are alternative transportation options available.